Hello, welcome to this video, Logistic Regression and Text Classification. So logistic regression is a classification algorithm that predicts the probability of an outcome by passing a linear combination of features through a sigmoid function. Because the output is probably between 0 and 1, we can use something called a cross-entropy loss or log loss to measure how far the predicted probability is from the actual label, as this penalty scales exponentially for confident but wrong guesses. To minimize this loss and find the optimal weights, the model typically employs gradient descent or its faster variant, stochastic gradient descent, which iteratively updates parameters based on the direction of the steepest error reduction. So in order to get a good grasp of this video, it's good to have know certain subject matter, and I cover it. In this video, one chain rule, this covers sigmoid function. It actually derives it from scratch. Cross entropy loss, gradient descent, and stochastic gradient descent. So let's set up the classification problem. First, we've got the data. Then we set up the classification function, which is computing y hat using wx plus p, given the probability of y given x. In other words, the conditional probability. And here the sigmoid function is used, which is 1 over 1 plus e to the negative x. Logistic regression is supposed to predict the probability. So we put the linear function inside, right? So we're calculating a number from 0 to 1. Then we define the loss function, which is a binary cross entropy loss. We can see this here. For those of you that know a little bit of statistics, it resembles a little bit of, it resembles a Bernoulli. Y log y hat plus 1 minus y log 1 minus y hat. Y hat would be the predicted value, y being the actual value. The cross entropy between true probability distribution and the predicted probability distribution. And then finally, we use stochastic gradient descent. And the objective of this would be to find the values of W and B that minimize the loss. Here, it's important to note that 1 over n is not used. We calculate the gradients, which is y hat minus y times x for W, and for B, it's y hat minus y. And then we use the update rules to get W and B. Eta is the learning rate that you could set to optimize a run. So I'm going to review quickly gradient descent and stochastic gradient descent. Gradient descent optimizes weights using all the data to minimize the loss. Right, so we're using all of it, all of the data. Stochastic gradient descent optimizes weights using samples. So after each iteration on a different sample, basically we get the weight, the optimal weights. And if you average the loss or gradient from many random SGD steps, you get the same result as computing the loss of the gradient on the whole data set. So SGD is like taking noisy guesses that are correct on average. So here I'm going to be showing basically the setup, but through a diagram. So we've got here the features x1 to x3. This is just an example, and B being the bias. We have the weight layer here. And then we have this summation where we do Wx plus B. We take sigma Wx plus P, which we saw earlier. This I didn't talk about. This is a threshold function, right? So we can have a lenient where greater than 0.5 or a more strict version greater than 0.8 is 1. Okay, so this will calculate the probabilities, the sigma Wx plus B. But then we're at a point where we're like, okay, what is the threshold? What do we decide on to have it equal 1, right? 1, 0. I mean, if we want to give an example, like hired or not hired, what's the probability that we would assign, right? If we want a stricter threshold for an individual being hired, we want the model to output something like 0.9. If we're not that strict, it could be 0.5. So this has real world ramifications in terms of what you decide to use, right? It could affect people's lives. It could affect like what kind of say, for example, another example is something like a tweet, right? Or spam, or having an illness, right? So freedom of speech can be highly subjective. For example, one person might consider something another person considers mild hate speech, right? So it's important to kind of realize that, right? Like if Twitter decides something is hateful in a language, I mean, they're probably tweaking some number and saying, okay, this surpasses our threshold for what we consider decent speech. And they could basically, censor you. So this is kind of the idea that's being used. So that will give you a hat ultimately, right? 1 or 0. Now, finally, we could use the cross entropy loss and gradient descent, right, gradient descent or SGD to update weights by minimizing the cross entropy loss, right? The backward pass computes, the forward pass predicts probabilities, the backward pass computes gradient of loss with respect to each weight. So this is how our weights ultimately get optimized and the loss is minimized, right? The goal is always to minimize the loss. This diagram was inspired by a person by the name of Sebastian Rachka. He's a AI engineering professor, I believe. So let's talk a little bit about feature engineering. This is kind of a segue into something that I'm going to be showing you later with logistic regression and features. So bigrams and trigrams can be used as features in a model, right? The prediction power should grow proportional to the increase in the amount of words used. So that would make sense, right? I mean, if you have more words, like a sentence, for example, that would probably be more descriptive than a word, okay? The man jumped over the fence would be probably more descriptive than just the word fence, right? So the bigrams and trigrams, you increase your vocabulary size, it becomes more descriptive and as a result, more predictive. So usually when you're working with text, you will have to convert words to counts. ML models will recognize numbers, not words, and that's important as well, right? The reason why we do all of this, or we convert things to numbers, is because ML won't recognize it if it's just text. This is another important thing that people can do to convert text into numbers. They're called indicator variables, 1 or 0, yes or no, hired or not hired, right? So that's pretty indicative. It gives you some extra understanding of the text that you're looking at in a quick summary type way. So you could check out the ideas of n-gram languages models more if you're interested in this video that I've got. So I'm going to be giving an example of sentiment classification, right? Using logistic regression as an example. And we were just talking about feature engineering. So we could extract features from text. And in this example, I want to find the general sentiment of Trump's tariffs on X. So we've got this individual, Spencer Fernando, and he's saying, as for Canada, Trump's latest tariff threat and ongoing erratic behavior further vindicate the Canadian government's move to deepen trade with our trading partners. Those who continue to blame Canada for Trump's unreliability should keep in mind that nearly every major US trading partner is also looking elsewhere. Trump, not the Canadian government, is responsible for the situation, and Canadians should stand together as our country fights to strengthen our economic foundation. So this is in general, quickly reading this, it looks pretty negative, but how do we parse this tweet into features? So we could see we highlight in red basically these negative words, right? There's probably more in there, but these are the ones that I've ended up selecting. Then we've got some other like words, deepen trade, stand together, strengthen. These are positive, right? We've got these bigrams, deepen trade, stand together, but in general, the yellow is positive. And then finally, we've got like a negative, which is a yes or no indicator type variable that I discussed earlier. We've got 3 of those, 3 positive, 5 negative, and 1 indicator variable. So now that we have these features, let's use a regression. Let's use a logistic regression. So here's a logistic regression example. We're going to tabulate everything that we've done and shown earlier, right? With the count positive words, we have 3. Count of negative words is 5, and then indicator variable 1, which was not in the doc, and 0 otherwise. Let's assume that the weights are learned already, okay? So we have py equals 1 given x, sigma wx plus b, and then we put that in to this function, right? The weights, right, are 2.5, negative 1.5, negative 1.2, and then we're multiplying it by the features x, which is 3, 5, 1, and then we're adding the bias term plus 0.1. We get that, we get sigma 1.4. Convert logit into probability. We do that using the sigmoid function, and we finally get 0.8. If we want to find the opposite of 1, right, y equals 1, say like negative, it's generally negative, that's what we want to classify. We could do the opposite and subtract that to get 0, okay? So the sentiment classification is 1, it's negative, 0, it's positive. You could do the inverse as well, right? You could do 0 is negative and 1 is positive. So it's up to you. in this. It's ultimately up to you how you want to define your study or your analysis. So we did one example. Now what would we do if it's stochastic gradient descent? We can consider tweets as individual samples. So it's not just Spencer, we would do multiple. We would use multiple tweets, and in each tweet, we recalibrate the weights, right? Whereas in gradient descent, we would use all of it, right, to get the weights. So the weights are relearned adjusted sample by sample over many tweets. This causes the weights to gradually converge, but the updates are noisy. And I mentioned that earlier because each tweet is just one sample. That's why learning rates and sometimes mini batches are used to stabilize training. So here's another example of SGD classifying toxic and non-toxic tweets. So SGD minimizes cross entropy by adjusting, optimizing the weights. And this is what I've been saying. Here we've got this algorithm, like the SGD, going through each of the tweets, and it's basically updating it to see whether it's toxic or non-toxic. On the y-axis, we got the cap locks ratio, right? And then on the x-axis, the number of exclamation marks. So the more you see of cap locks and the more you see of exclamation marks, it's probably going to be a toxic tweet. So here's some examples. Tweet A would be I'm angry. That's 100% caps. That would be classified as pretty toxic. This is a very long and detailed explanation of why I'm currently feeling slightly frustrated and perhaps a bit angry. That's only 5% cap, so maybe it won't get classified correctly. This sucks, awful. This is obviously a toxic tweet, and it go to the right, far right. So SGD is basically going through all of this and classifying. Okay, and it's optimizing the weights. So each time a black circle highlights a single tweet, the model calculates the error, the cross entropy loss, and immediately updates the weights to move the boundary towards the correct side of that specific data point. This illustration wasn't drawn to scale, but that's the idea. Basically, you want to push the toxic tweets to where they are actually toxic, and the non-toxic tweets to where they are non-toxic. And you can see from the feature engineering, the number of exclamation marks, the lower that is, and the capital locks, the lower that is, it's probably going to be not toxic. So thank you very much, and hope you have a great day.